Hey there, AB students. It's me, your teacher. I'm going to make a video about continuous functions. So hopefully this will be brief and to the point. So continuity. Here, continuity, this word is talking about the word continuous. What does it mean for a function to be continuous? Well, intuitively, a function's continuous if you can draw it with its graph without lifting up your pen. So for example, something like, here's a function. I've just drawn the graph of this function without lifting up my pen. So intuitively, we think this is a continuous function. Here's another example. This function, to draw its graph, I needed to lift up my pen. So this function is discontinuous. Discontinuous. That means it's not continuous. So, a warning here. Continuity has nothing to do with something else called local linearity. So continuity is different from local linearity. So what do I mean by this? This function right here, it's continuous. I drew it without lifting up my pen. However, it's not locally linear here. Not locally linear at the spike. So continuity is totally different from local linearity. So now that you have an intuitive sense of what it means for a function to be continuous, let me give you the definition. So there's three parts to it. We say a function is continuous at x equals a if you need three things to be true. First of all, you need f of a to be defined. Second of all, you need the limit as you approach a from the right of the function equals a limit as you approach a from the left of that function. If these two limits are equal, then this tells you that the two-sided limit as x goes to a from both sides, that this exists. So these two things mean the same thing. If this limit exists and equals this limit, which also exists, then the two-sided limit exists. And the final thing is that you need that when you take the limit as x goes to a of the function, you just get f of a. So a continuous function is exactly a function for which the limit is the same thing as evaluating the function. We ask this question a lot in class. Well, this is the definition of what it means for a function to be continuous. So pause the video here, write these down, think about them. This is the definition you'll need to know for my class and for the AP test. So the next question you should think about is, how do I tell if a function is continuous? Well, it turns out most functions are continuous wherever they're defined. So whenever you plug in something in the domain of the function, then that function is continuous. So for example, a function like ln x, this is a function that has domain x bigger than 0. So this function, wherever it's defined, whenever you plug in an x in the domain, it's continuous. X squared minus 1, that's an example of a continuous function. For example, sine x, cosine x, these are all continuous functions. Tangent x is a continuous function when it's defined. So the domain here is that x should not be equal to pi over 2, 3 pi over 2, any of these bad values. So wherever it's defined is continuous. The only warning I want to give you about continuous functions, the only thing you need to watch out for are piecewise functions. We'll see an example of this. Piecewise functions, you need to check if they're continuous. So sometimes discontinuous at the breakpoint. What's the breakpoint? That might be where the two different pieces of the function come together. So I'll show you an example of that right now. So here's a function, fx equals 1 divided by 2 minus e to the x, where is this function discontinuous? So to answer this, it's going to be discontinuous where it's not defined. Where it's not defined. How do you figure out where it's not defined? Well, this thing has a denominator. Set that equal to 0. So 2 minus e to the x equals 0. So that gives you e to the x equals 2. So x is equal to ln 2. So this function is discontinuous at x equals 2. And it's going to be continuous everywhere else. Here's another example of a function. This is a piecewise function. I told you you have to be careful about piecewise functions. Is this function continuous? Well, both pieces by themselves are continuous. The only thing to check, so you need to check the limit as x approaches 1 from the right of the function. We want to know, does that equal the limit as x approaches 1 from the left of the function? So as x is going to 1 from the right, I'll use this piece. As x is going to 1 from the left, I'll use this piece. So we want to know, is this equal to this? Well, this is a continuous function by itself, so I can just plug in x equals 1. I get 2. We want to know, does 2 equal question mark? What do I get when I plug in 1 into here? I just get 1. So the answer is no. So this function is discontinuous at x equals 1. So therefore, fx is discontinuous at x equals 1. So that's the conclusion we draw from this little argument. Okay, so that's all the examples I have for now, but there's something else I want to talk about. If a function's not continuous, then it is discontinuous. And it's really, there's actually 4 types of discontinuities. So I will draw a little picture for each of them. A removable discontinuity might look something like this. Here's one example, and let's call this x value a, or possibly something like this. Without the filled in hole. So a removable discontinuity happens when the limit as x approaches a of the function exists. So in both these cases, the limit exists, this limit exists, and this limit exists, but does not equal f of a. In this example, f of a is different from that limit. In this example, f of a is undefined. So this is called a removable discontinuity, and they're kind of the nicest discontinuities because they're really easy to fix. You just kind of, if you were to redefine this function here to fill in that hole, then it would become continuous. So a slightly more crazy type of discontinuity is a jump discontinuity. You've seen these before. A jump discontinuity might look something like this. And this is the value x equals a. So what's happening here? Here, the limit as x goes to a from the right of the function is not equal to the limit as x goes to a from the left of the function. So you'll often see jump discontinuities with piecewise functions. The third type of discontinuity is an infinite discontinuity. This is the same thing as a vertical asymptote. So here at x equals a, maybe you have a vertical asymptote. So this dotted line is x equals a. Maybe your function is doing something like this. So an infinite discontinuity happens at a vertical asymptote. and it's going to be when limit as x approaches a from, in my example, the negative direction equals plus or minus infinity, or it can be when x approaches a from the positive direction. This should equal plus or minus infinity. So this is exactly the same thing as a vertical asymptote, and an infinite discontinuity is no different from a vertical asymptote. Even though this function is defined at a, it's still discontinuous there. To draw it, I have to lift up my pencil, bring it back down here, then keep drawing. And the fourth type of discontinuity is the craziest one. You've seen it before. It's an oscillatory discontinuity. The classic example is y equals sine 1 over x. Graph this. This is a wave. And it's getting crazy at 0. So what's happening here is that the limit, even just the one-sided limit as x goes to 0 from the right of the function, does not exist. As x gets close to 0, the y values are moving up and down so quickly, they're not getting closer to anything because they keep just moving up and down. And this is an oscillatory discontinuity. So that's everything I have to say about continuous functions. Take notes on this stuff. You might have a quiz.